Now let us see how Maxwell's equations predict the propagation of electromagnetic waves. In empty space, or vacuum, there are no charges and no currents. So ρ is 0, and J is 0. Maxwell's equations simplify to these four source-free equations. To find the wave equation, we take the curl of Faraday's law. On the left side, we use the vector identity for the curl of a curl. Because the divergence of E is 0 in a vacuum, the first term vanishes, leaving minus the Laplacian of E. On the right side, we swap the spatial curl and the time derivative, and substitute the Ampere-Maxwell law. This gives minus mu 0 epsilon 0 times the second time derivative of E. Cancelling the minus signs yields the classic 3D wave equation for the electric field. An identical equation holds for the magnetic field. Let us look for a simple plane wave solution traveling in the z direction. With the electric field polarized in the x direction, we substitute this cosine wave into the wave equation. The spatial derivatives bring out minus k squared, and the time derivatives bring out minus omega squared. This requires that omega over k equals 1 over the square root of mu 0 epsilon 0. This ratio is the phase velocity of the wave, which is exactly c, the speed of light. What about the magnetic field? We find it using Faraday's law. In a plane wave, spatial derivatives become multiplication by ik, and time derivatives become multiplication by minus I omega. Faraday's law then becomes k cross E equals omega b. This cross product tells us two crucial things. First, the magnetic field is perpendicular to both the electric field and the direction of propagation. The wave is strictly transverse. Second, the magnitude of B is simply the magnitude of E divided by C. Let us visualize this propagating wave. The wave travels along the z-axis. The electric field oscillates in the vertical plane. The magnetic field oscillates in the horizontal plane, which we draw tilted to give a 3D perspective. Notice that E and B are perfectly in phase. They reach their maximums and cross zero at the exact same locations. As time moves forward, the entire pattern shifts to the right at the speed of light. Finally, how does the wave carry energy? The energy flux is given by the Poynting vector, S, which is E cross B divided by mu 0. Because E and B are perpendicular to each other and to the direction of travel, their cross product points exactly in the direction of propagation. The electric and magnetic fields continuously exchange energy, but their sum, the total energy density, travels forward through space. This self-sustaining dance of electric and magnetic fields is what light truly is.